Good morning. Good morning. Welcome to another episode of Xa Talk Show. And today we are going to talk about this wondrous subject of geometric inversion. So let's go to Curves, my plane curves website, a visual dictionary of special plane curves. Now, this is a project of geometric inversion. Let's go. Let's see. It's a topic here, geometric inversion. And I'm going to show you how this image, this beautiful image is made. This is a geometric inversion of a grid, of a rectangular grid, just like vertical lines and horizontal lines. After the transformation of the geometric inversion, then you get this picture. And this topic is related to quite a lot of things in mathematics, in complex inversion, in Riemann sphere, in the complex function 1 over z, which is inversion. It's called inversion, and Mobius transformation, and stereographic projection. It's all tied together, and geometric inversion is kind of it's actually the heart that ties them together. Yes, it's one of the fundamental part of it. Let's see if I'm actually alive, because sometimes I make mistakes. I'm live. Good. So if you are new here, say hi. This is my talk show, and what I'm going to talk about and the quality of my talk depends on your feedback, your comments, your opinions. Okay, just put it here. Um, so this topic, avocadoras, has been asking me to do. So I'm gonna. We haven't done a math talk for a while, so we're gonna do it. And by the way, a month ago or so, we did a talk on complex numbers, the origin of complex numbers, and so you might be interested in watching that video. The origin of complex numbers. It's not what you think. What you learned in school is wrong. They in school they teach you how complex numbers is invented so that you have the solution to uh, x squared equals to -1. No, that's not true. But anyway, so let's talk about geometric inversion. But I want people to come on. So how many people are watching? 3 people. Great. So we can begin. And today, let's try to use. I got this pen tablet, so let's try to make use of that. Use of it. This is a Huion pen tablet. With this, I can write on it. Let's start GIMP and let's see if we can start to lecture on mathematics and geometry. Oh, it's the eternal subject. So let's see. So let's go to geometric inversion. Let me write out the topics, and also I need to update this. So you know so uh, let's see. Xatalk show. Create a new page here. Okay. Hold on a second. Let me create a new page. Talk section, and there it is. Xatalk show. And copy that, switch, paste, and the topic is going to be about, we're gonna talk about geometric inversion. And I'm writing out the topics so I don't forget. We're gonna cover these topics. I'm gonna teach you, in essence, teach you about these topics. geometric inversion. It's beautiful. You see, even from the art perspective, just for decoration. For example, if you have a house, or you eventually you are going to have a house maybe, and you're gonna decorate your windows. You can decorate your windows like that, like a stained glass window, or your garden, or your tiles, bathroom floors, and that's going to be spectacular. So I'm gonna show you what those means. So and and stereographic stereographic projection and Riemann sphere complex plane uh, and the complex function 1 over z. Okay, so these are the topics I'm gonna talk about. Okay, so let's and again, the more comments you have, the better my talk will be. So do comment on the here, in the chat box. So okay, let's start then. Hold on a second. Let's get that correct. Listify. That's right. These are the topics. And okay, so let me show you this. Okay, so this hi Dion. Good morning, Dion. Do you know anything about threading macros? Have options about them? What do you mean threading macros? Is like keyboard macros, Emacs keyboard macros, or do you mean Lisp macros? But today we're gonna focus on math though, so I'm gonna focus on geometry and math. Uh, we're gonna, we gonna this is gonna be maybe an hour. So let's talk about geometric inversion. So geometric inversion is a transformation. Okay, that means it's like okay, there are transformations. For example, reflection. You know what's a reflection? Let's go to Wikipedia because that's uh, so so the so in mathematics there's a thing, especially in geometry. Okay, a branch of math, especially in the context of geometry, you have the concept of so-called transformation. Okay, now that word is used in math in lots of places, and the meaning may differ slightly, but in general, a transformation means basically a map. Okay, or as a programmer, it means a function. That means given an input, you have output. But in math, it typically means, especially in geometry, it typically means you have a space or a plane. Okay, then you go through a transformation, meaning in a plane, you have points in the plane, and after the transformation, the points you move the points to somewhere else. So each point has a position, in the plane originally. After the transformation, it becomes somewhere else, another position. So this thing is called transformation. So what are some examples of transformation? Transformation, for example, Uh, for example, we have reflection, we have translation, we have scaling, uh, we have rotation. Now, these are some of the examples of transformation. Now, and these are very simple. You can understand. So let's see. I need to. Yeah. So let's get to. So reflect. For example, you have a plane. Oops. That's not what you want. So hold on a second. Let me adjust. I want a pen, and I want the dot size is going to be 4 points. 4 point is good, and I don't want dynamic. I want pressure size. Actually, I want dynamics off. Okay, so that's good. So start a new one. So reflection, if for example you have a plane, okay, so let's see. Okay, so this gotta be here. So you have a plane, x-axis, y-axis. So this is x, this is y, and the reflection is means, for example, if you have a line and you have a point here, A, B, and reflection, it just means it becomes over here. Let's say A dot B prime. Okay, this is actually slow due to anyway. So this is what reflection means. It's like a mirror reflection. The line can needs not to be vertical. It can be like horizontal. So this point becomes this point. This point becomes this point, and that is point by point. And you could have a circle. If you have a circle here, then it gets mapped to over here. If you have a triangle, let's say this, and it becomes like that, something like that. Okay, so this is called reflection. Now again, remember, reflection is a transformation. You can think of it as a function. So in geometry, given a plane, you apply this transformation, then a circle becomes over here. A transformation over this line. This is a function. This is mapping. This particular transformation is called reflection. Now that's simple enough. Now translation, okay, these are some examples of transformations. Translation just means move a point to some other place. Um, Actually, let's go to Wikipedia because that is actually easier. The arrow macro from closure. Yeah, we can talk about that next episode about Lisp macros. Um, and arrow functions. But anyway, so let's go back to, so let's see. Well, let me quickly get over these so we can start to talk about inversion. So transformation is just a function, a map. Okay. So the four of the simple examples of transformation is reflection, translation just moves something from here to another place by a vector. That is, you move horizontally by by x, by a number, and you move vertically by a number. So it's like you can move something to anywhere. Like a point, you start with a point, and you can move it to, for example, x to the right 2 units, y up 1 unit. So you move by the vector 2 1. So basically that becomes, it's like it's moved diagonally, and so that means translation. That means you move the point to somewhere else. And there's a scaling. Now of course you know what is scaling, right? Scaling is like, for example, let's go to the Wikipedia article on reflection. Click. Okay, and the reflection, let's hold on, magnify. Now let's magnify. Now magnification is actually the geometric process of scaling. So we actually covered, the transformation. You see how each point has a position originally, but after magnification, it becomes somewhere else. Now this process in math is called It's called scaling or it's called dilation. Okay, and it's one example of the transformation, geometric transformation. So let's see the article. It there. So here is a article on reflection. You can see Wikipedia examples. Now, so scaling is called dilation, okay, or known as dilation. And another thing is about rotation. Now everyone understand rotation. Now uh, these four these four transformations together is called isometry. Now that's important. That's very important concept in geometry when you study geometry in math. Okay, now I'm talking about geometry. This is not geometry. I mean, when you think of geometry, you think of most of you are probably thinking of elementary geometry. Circles, triangles, trigonometry. The volume of a circle. The area of a circle. That's geometry, but that's kind of high school geometry. But here I'm talking about transformation and these simple examples, although they are very simple, but these are the beginning of rather advanced geometry in math. Okay, you'll see this concept applied. So anyway, so I have given you four examples of very simple transformation. These four specific transformation is called isometry. Now we're starting to get into jargons. This word isometry. Let's go to Wikipedia and we can see isometry. Now let's read. Okay, in math, an isometry is a distance preserving transformation between matrix spaces, usually assumed to be bijective. Now that's a lot of jargons, but and we have the jargon matrix space. But basically, if you are in a plane, it just isometry is just one of the reflection or translation or scaling or rotation, or combination of those. Because they are called isometry because they have the property of distance preserving, meaning that if you have 2 points in a plane, there's a distance between them. Now, after you do the transformation, the points will become somewhere else. Okay. However, the distance you again measure the distance between the points, they will be the same as when you before the transformation. So that's what distance preserving means. Now this is important because this is one of the property uh, of isometry. These four transformations are called isometry, and you have this property. Distance preserving is one of the properties of these four particular transformation. But later on, you will start to see other properties. For example, there is a angle preserving property, uh, which is called conformal map. Okay, which is related to complex analysis. We'll get into that. Geometric inversion. Now, the topic we are going to talk about, geometric inversion. Okay, this one. You see this beautiful but weird shape? Now that is a transformation of a rectangular grid. For example, you start with this image. Okay, this is just a simple rectangular grid. After the transformation, meaning points are moved to some other place according to a function. Then you get this picture. You get this weird looking picture. That's a transformation, and this particular transformation is called geometric inversion. And I'm going to explain how it is done. What is the rules? Okay, but like I mentioned before, this is an example of a transformation. Just like the reflection, translation, scaling, and rotation are transformations. Okay, and those transformations are called isometry, like we talked about. They are isometry because they are distance preserving transformation. They are called isometry. And let's let's make sure if I didn't get it wrong. If I okay, you see you see how the article. I mean, if you never studied math, as I assume you haven't, you are a programmer. So you start to see these words, isometry, manifolds, uh, you know so so that gives you a flavor why how math gets become advanced, but the idea is pretty simple. Then you have anyway, so let me make sure I got this right. Actually, so formal definitions, yeah, so distance preserving map is called isometry. By the way, map, the word map and transformation have the same meaning. Okay, a function or map or transformation in math, they pretty much have the same meaning. Which word to use usually depends on context. For example, if you're talking about geometry, usually we use the word transformation. Okay, if you are in algebra, usually you use the word function. Okay, so but basically they mean the same thing. So let's see, isometry. Okay, but anyway, so I'm pretty sure these four transformations, the complete list of transformations that are distance preserving in the Euclidean plane are these four: reflection, translation, scaling, or rotation. Um, yes, I'm pretty sure. But I do not see it listed in Wikipedia because this article is general, because you have to go to the article that talks about uh, isometry in Euclidean plane. Because Wikipedia becomes larger and larger. So anyway, it's somewhere it should mention rigid motion. Okay, rigid motion is another word for isometry in Euclidean plane. Anyway, let's not go into that. It gets complex. But anyway, so we have transformations, we have isometry. Now let's talk about geometric inversion. Now, geometric inversion. Okay, now it's a transformation. Let's see how long I've been talking. So I want. Okay, so let me get. Um, okay, so how is it defined? Here is how geometric inversion given a fixed circle. Now suppose you have a point P in the plane somewhere. Okay, now we want to know where does P lies after the transformation, after the geometric inversion. So again, remember geometric inversion is always with respect to a given circle. Just like when you have a reflection, it's always with respect to a given line. And translation is always with respect to a vector, like a direction in horizontal axis and vertical axis. That's translation. And scaling is always with respect to a number, and like how much you want to zoom in or how much you want to zoom out, with respect to a number. Rotation is also always with respect to a number, like what degree you want to rotate. Also with respect to a center, like with which center, but usually we assume it's an origin. Like given xy axis, you have let's see here. Uh, Close that. Given the xy axis, you assume the origin is the center of rotation. So anyway, these are transformations. So back to inversion. So inversion is always with you have to given a circle, a fixed circle. So given a point P, how is it transformed? Now from the center, let's say center of the circle is O. Okay, suppose that's the origin, point 0, 0. So suppose the circle has radius r. Okay, from here to here, it's a radius r. And okay, so the inversion is defined by a point Q in a plane such that the line from O to P, the distance from O to P times the distance from O to Q is equal to r squared. R is the radius of the circle. Uh, does that make sense? Okay, guys, comments. Okay, I only have. Okay, I got 5 people watching. Comment. Comment. You comment, I talk better. Okay, so do you guys see the definition of inversion now? So inversion given. So first of all, given a circle, um, given a circle, you have a radius r, and given any point P in the plane anywhere, you want to find out where is the new P, after the transformation. So the way you find it out is that you draw a line from point O, the center of the circle, to P. Then you have a distance O to P. The new point, which is the uh, inversion of P, is a point Q such that the distance from OP multiplied by distance OQ is equals to r squared. This formula. This formula. Okay, so maybe I need to do some interactive examples. So let's do that. Let's see if we can do that. So here is a interactive example written, using the GeoGebra. So this point, you see, first of all, we are given a circle, we are given a circle, and we are given any point P in the plane. And you can see the point Q is the inverse of P. Now, in this interactive application, you can see how they relate, P and Q. And the point Q, as I mentioned, it's determined by, you draw a line from O to P, and the distance OP times OQ is equals to r squared. But anyway, from this you can see the further away P is, the closer is Q to O. Now, what and let's hold on a second. And what if, okay, so we can also actually change the circle, but let's not do that. Anyway, let's change the P. Okay, wait, something is wrong. Hold on a second. We want to, okay. So okay, so we can see that as P moves far away, Q becomes closer to the center of a circle. Now, if P is on the circle, then its inversion point is itself basically on the circle too. Now, if P is inside the circle, Q moves far away. So the point P and Q are kind of like a mirror of each other. They are kind of mirror images. So you have this line outside of the circle, and you have this line inside of the circle, and any point on the circle, they kind of mirror each other. So this line outside the circle is infinite. They go to infinity. But all these infinite points are mapped to inside the circle segment. You can see that. You see how they are mapped. So, and what if the point P is on the center of the circle Q? basically you can see that as P moves closer to the center, Q moves further away. So when P is actually at O, its inverse is, you can think of it, it's infinitely far away. It's like the infinity at, everywhere. It's like the infinity. Okay. So here is where you get the concept. The concept of infinity happens. It just happened naturally. In math, like when you see infinity or a fourth dimension, sometimes you wonder, where does this concept came from? Like what the hell? So, but here, from an example, we can see the concept of infinity just happened naturally. You see, because as let me move. Let's change the size of the circle so uh, we can see more clear examples. So if we move the P inside, the circle, Q becomes outside. P gets closer to O, the center, Q moves far away. And you can see as P gets closer and closer to O, the Q moves further away. So now you naturally get the concept of infinity. In fact, it's you get the concept of a point in a plane that is that is infinitely far away from the center of the circle. In fact, doesn't matter what direction. Like in doesn't matter what direction. So it almost seems like, you know the infinite borders, of the plane is one point, infinity. I mean, it's like there is a magical point called infinity that is mapped to the infinite border of the plane. So anyway, so this is the definition of geometric transformation. Now we are looking at this geometrically, and you can see how they correspond. But algebraically, it's defined by this equation. Distance OP times distance OQ equals to R squared. Okay. Now that concludes the definition of geometric inversion. Now let's recap. Geometric inversion is a transformation. What does that mean? That means given a point in a plane, you have, after the transformation, you have a new position for the point. Now, every point has a corresponding point, except the center of the circle. Now, when the input point is at the center of the circle, we kind of say, either, there's two ways to approach that issue. One way is that we just say, oh, that's not defined. It's like undefined. It's like 1 divided by 0. We just say we don't allow it. So geometric inversion is a function such that every point in the plane gets a new position except one of the point. Okay. We say that the function is not defined on that point. That's one way to do it. Or another approach is to say that we kind of imagine there's a point at infinity. So if the input point P is the same as the center of the circle, we say that the result is a magic point at infinity. Okay, we don't know what it means, but that's kind of how we can approach it. And in fact, that's a lot of math approach things. When we approach, infinity is a very curious concept in math. But here we have an example. We have given definition of geometric inversion, and we have also uh, touched upon. We have also encountered this infinity concept, and so far we have two approaches. One is that we just say it's undefined. Okay, we define the transformation to have one special point that's just undefined for the function. Another approach is that we kind of elaborate or think of there's a point at infinity. Now this is important, and this is very curious. You might think this is getting kind of messy and kind of you know strange, but math is full of these strangeness, and it's also how it becomes interesting because this point of infinity has significance. Okay, it's critically important in math. It's like when in as a programmer or as a if you are interested in AI, you might have heard of the concept of singularity. Okay, the singularity concept came from math, and what it means is also kind of what we are dealing with right now. It's like 1 divided by 0. It's like some kind of infinity, some kind of things that's either undefined or it's infinity, some sort of magic. Okay, that all came from math, and we have just encountered one such example. Now, okay, now we have defined geometric inversion. I hope I'm not actually repetitive. Okay, I'm losing, I'm losing watchers fast. Okay, let's read the comments. Good morning, Norman. So, if P is the circle origin, the inverse is effective of the visible canvas. That's correct. Yeah, yeah. So it's kind of it just went infinity. It went to infinity. Yes, yes. Now I'm gonna talk this now. So today we are talking about geometric inversion. Now this is related to stereographic inversion, which actually connects to this strange concept of infinity, like the point went out of canvas. It connects them in a coherent way, in a such a beautiful and coherent way. I hope to explain next. Okay, we'll come to that. So first of all, let's go to let me just show you the stereographic projection. Okay, so you can see a picture of it. Now remember the connection between stereographic projection and the inversion we just talked about, geometric inversion, is that it makes this concept of a point going to infinity concrete, like we can actually see it. Now at this moment we cannot see, like what do you mean a point went to infinity? Like we cannot see it because the point just went far away. But now when we do geometric inversion, when we do stereographic projection here, uh, we can actually see the point and everything makes sense now. Here's what we're gonna talk about. This is a stereographic projection. Now this is 3D. Okay, this is three-dimensional, but the geometric inversion we just talked about is 2D. Okay, this is 2D, but we are going to connect them together so you can see how they connect together. So anyway, before we talk about stereographic projection, let's come back to geometric inversion. Let's cover a little bit something, tie them together. So geometric inversion, like the geometric transformation we talked before, the isometry. There are many extremely interesting properties of geometric inversion. Now, remember this thing. When we are doing this, we are mapping one point to another point, right? I mean, it's a transformation. So, given a point, we have a result, which P becomes Q. So, in the same way, we can actually start to draw a circle here, a circle or a square or a photo of yourself. Like you can put a photo of yourself here, and you do the geometric inversion on the points on the circle on the photo, and it will be transformed into inside of this circle in a weird shape. Basically, given any image on the plane will become some other image, because remember this is geometric inversion is a transformation, meaning that it maps all points to some new points. So now you know the rule of transforming one point but you can apply the rule so you can transform any picture, like any photograph, any like a picture of myself. It be, so you get interesting picture. This is an example. This example is transforming a grid, just a rectangular grid. It becomes this. So there are many interesting properties. Now remember before the isometries, they have a interesting property, and that property is they are distance preserving. That means given 2 points, they have a distance after the transformation, such as reflection. The distance between the 2 points, their new positions, remains the same. They are called distance preserving. Now, geometric inversion is not distance preserving, obviously, because if you look at the grid, you know, in a grid, each point, between the squares after the transformation, they are not the same distance, anymore. Some becomes further apart, some becomes, closer together. But however, there's an extremely curious and important property. They are angle preserving. you know, that is okay. For example, this is a grid. Suppose we begin with this picture, this image. In math, we call it image. Okay, we call it pre-image. After the transformation, we call the image. Okay, so this is pre-image. We're gonna apply a transformation, and what we get is called the image. Okay, but anyway, so we start with this picture, this image. Okay, so you can see. So what we mean by angle? Angle means, for example, in this picture we have the lines, and they form 90 degrees. Okay, they form 90 degrees. After the after the transformation, after we apply this geometric inversion, you know, for every point on the grid, every point, not just the cross intersections, but every point, we get a new picture. And that picture, what does that picture looks like? It looks like this one. Okay, so this is a pre-image, this is an image. So so you can see lines become circles after geometric inversion. Yes, that's a theorem. Okay, uh, lines become circles, and actually circles become circles or lines. It gets extremely interesting, and there's a very important and interesting property, that is angle preserving, meaning that you see here we have lines, they form 90 degrees angles. After the transformation, uh, you see the lines become circles. Okay, and all the circles, when they intersect, their intersection is always also 90 degrees. You see, here we have 90 degrees intersection, here is a 90-degree intersection, here is 90 degrees. Every intersection remains 90 degrees. So that means, this is very curious, because we have this transformation, geometric inversion. It looks like on the surface things becomes, warped out of shape. But actually, all the angles, doesn't matter it's 90 degrees or any other degree, any intersection between two lines are preserved. The angle doesn't change. It remains whatever angle it was before. So that is a fundamental. This is very critical importance when you study complex analysis. This is one of the most important thing, because right now we are talking about right now. So far we've talked about just plane, real numbers in a plane, x axis, y axis, points in the plane. We are not talking about complex numbers, but as you know, math is all related. When you study complex numbers and complex analysis, it's the whole thing is fundamentally based relates to this. It's based on the idea of geometric transformation and angle preserving. By the way, the jargon in math for angle preserving transformation is called conformal map. It's called conformal map. Okay, let me write it down, because if you go to Wikipedia and you look at the word conformal map, okay, that's the word. Let's go to Wikipedia, and you can start to see, it relates to the complex analysis. The whole branch of math is based on this idea. Mobius transformation, conformal map, and derivatives of complex functions, and so on. Conformal map. Okay, let's go to Wikipedia. You can read it. Offline. I hope I'm giving you a good introduction, so that now when you look at these jargons, you start to understand, because before, when you read this, you may not see what's going on, but now you do. But anyway, so conformal map. So anyway, let's go back to geometric inversion. So we were talking about, so geometric inversion is a transformation, and it has a bunch of very interesting and important properties. For example, circles become circles itself, and lines become circles or lines. Circles also become circles or lines. So basically, circles and lines are preserved. They become either circles or lines. For example, in this picture, let's open it. You see this yellow circle. This yellow circle is the inversion circle. Remember, geometric inversion is based on a fixed circle. We have to have a given circle. Now, this purple lines is the pre-image. Okay, these purple lines becomes these red circles, and vice versa. So if we start with these purple lines, after geometric inversion, they become these red circles. Okay. On the other hand, if we begin with these red circles, and after inversion, they become these parallel lines. So in geometric inversion, circle and lines are preserved. They become circle lines. Now let me show you another very interesting property about geometric inversion. Now, when we think of reflection, like reflection, let's go back to reflection. You see how, like reflection are like mirrors, right? Things becomes to the other side, comes to the other side. Now, geometric inversion is actually, you can also, it's actually, you can think of it as a generalization of reflection. Okay, why is that? Because look at this picture. You see, all points on the outside of the circle comes to the inside of the circle, and any point inside the circle comes to the outside. So this circle, this fixed circle is like the mirror. It's kind of a mirror. It mirrors everything inside to the outside, and everything outside to the inside. So geometric inversion is actually a generalization of reflection or mirror. Why? Because you can see as the circle becomes large. Let me see if I can make, okay. I'm trying to make the circle large. I cannot. Okay, I can do it here. I can. Okay, I can. This GeoGebra application is not constructed so that I can just drag to change the circle size. I don't think I can do that. Yeah. But anyway, what I'm trying to show is that you can see that as the circle becomes larger and larger, the inversion circle, imagine it gets larger and larger. It becomes infinite large. infinitely large, so that the radius becomes infinity, and the circle actually becomes a line. That is when this inversion becomes just reflection. So again, we have the concept of infinity involved. Just imagine the circle becomes large and large. You know, the radius becomes infinite, and the circle is curved, but now it becomes less and less curved. It becomes a line. Then you can start to see the left side is mirror to the right side. So that's kind of like that's a generalization of this reflection concept. So that's another interesting thing to think about. The geometric inversion kind of just warp everything inside the circle to the outside and vice versa. It kind of just mirror it. So interesting properties include, lines and circles become circles or lines, and yeah, let me show you an example. There's an interactive application again. Oh, high base. Okay. um, so here we have a geometric inversion of a. So this black circle is fixed. Okay, this blue circle is the circle we want to invert. So this blue circle becomes this red circle inside the circle. So we can move the blue circle around. So these two are inversions, geometric inversions of each other. So you can see circles actually become circles. At some point, they become itself. And you can also see how they become. You see how circles start to become a line when the radius becomes infinite. You see there? And it warps back. So this is the fascinating thing about geometry and math. So anyway, so that's so how do you know? How do you know circles become circles? I mean, can you prove it? Yes. So I have a proof here. You can read it offline. It's very simple. It's very easy to understand. Proof how circle and lines becomes themselves. So that's one property, and another property is that angle preserving called conformal map. So geometric inversion is a conformal map. Okay, that's all I want to say about geometric inversion. So I hope next I'm gonna talk about. Okay, I hope in 10 minutes I can cover how it relates to stereographic inversion in 3 dimension. And I hope that will be it for today. And there are other things like complex plane, Riemann sphere. We almost touch it. Like we are like almost here, almost there. They are like because all these topics are related together. Stereographic projection, Riemann sphere, complex plane, and complex function 1 over z. Now, stereographic projection is actually just a geometric inversion in 3D. Okay, we're gonna talk about we're gonna get over that. Let me show this. Yeah, this is stereographic projection. It's actually it is just actually a geometric inversion in 3 dimensional space. And the Riemann sphere is actually just this sphere of a stereographic projection. This sphere, when it's formalized into math, we call it Riemann sphere. It's actually just the extension of the complex plane, which is basically a plane with a point at infinity. That's how we tie it to the point at infinity. We can so a point at infinity is actually just the north pole on this sphere. Yeah. So we have complex plane, and we have complex function 1 over z. Complex function 1 over z is actually just the geometric inversion plus a reflection of the along the x-axis. So you have geometric inversion, you do that first, then you reflect, the whole plane over the x-axis. That is the complex inversion, the complex function 1 over z. Okay, so that's how they are all related. But let's talk about the stereographic projection, how they relate to geometric inversion. Okay, now as you know, this how so stereographic projection is it's a transformation, geometric transformation. It's a function that maps a point on a plane to a point on a sphere, okay, on a ball, or vice versa. So you can map a point on a ball anywhere on a ball. Imagine a football, and you draw a point on the ball. You want to have a corresponding point on a plane. The way you do it is you just put the ball. It's like put the ball, on a plane. Let's see if we can do that. Like that. let's let's see. So you put the ball on a plane. Then at the top of the ball, let's call it North Pole. You you draw a line to a point on a plane, or a point on a sphere. Let's start by a point on a plane. You draw a line, and the line will intersect the sphere, and that intersection would be the corresponding point to the point on the plane. So by this way, by this method, by this rule, by this function, this is how we have a map between any point on the sphere and any point on the plane. And this method, this rule, this approach is called stereographic projection. Okay, that's the name of it. Now, except there's one exception. What if the point on the sphere is at the North Pole? Where does that point become? Where is that point on the plane? Again, we have a situation just like before, just like the geometric inversion. We can either say, the North Pole is undefined by this transformation. Okay, it's not mapped to any point on the plane. Or we can say the North Pole on the sphere is mapped to a point, is mapped to some sort of a point at infinity, because you can see if you have a point on the sphere, you can see if you move the point on the sphere closer and closer to the North Pole, the corresponding point on the plane will be further and further away, such that if your point on the sphere is very close to the North Pole, then the point on the plane is like very, very far away. In this process, you can kind of see, you can kind of picture the ideal. So what happens if the point is, the North Pole? You can kind of see it actually become a point, some kind of magical point, infinitely far away. Doesn't matter what direction. So it's just a point infinitely far away. So mathematicians, what you do is that, so they just say, mathematician says, okay, imagine you have a plane, okay, a sort of ideal plane, and this plane is called Riemann Sphere, okay. So what does that mean is that you have a plane, infinite in all directions, but however, there is a point in the plane that's called infinity, the point at infinity. This point we call the point at infinity, okay? That is just a point infinitely far away that connects to the whole plane. In other words, when you look at the stereographic projection, you can think of the whole thing as just a sphere, okay? So now the whole plane mapped to the sphere, except except the sphere's got one extra point than the plane. That is the point at the top, the North Pole. But now we imagine the plane actually has that point. So the plane becomes some kind of ideal plane with one extra point added. That point is called the point at infinity. And now with the stereographic projection, that point is easy to understand because from this process you can see you can just think of the plane as a sphere. So by this magical means of projection, stereographic projection, now any picture on the plane, you kind of see the plane as a sphere, and vice versa. So anything you do on a sphere is kind of like correspond to the plane, and anything you do on the plane is corresponding to the sphere. Okay, now that is stereographic projection. Now this ideal plane we've been talking about with the extra point of point at infinity is called Riemann sphere. That's just the math jargon. Okay, now you can go and read that article on Wikipedia. This is the concept, what mathematicians call Riemann sphere. So for example, let's read it. So in math, Riemann sphere is a model of extended complex plane, the complex plane plus a point at infinity. Okay, that is what it is. So when you study complex analysis, basically you are studying Riemann sphere. And it's related to division by zero. So the extended complex numbers. So what is the extended complex numbers? Basically, that's just the plane we are talking about, with one added point called the point at infinity, and that point give us the meaning of 1 divided by 0 in the complex plane. So it ties to complex analysis, even though we haven't talked about complex numbers yet. Okay, but we are just talking about the geometry. So but you can see how they are all related. That's what makes math so interesting. So anyway, complex. So we covered stereographic projection. We covered inversion. Now, what's left to do is, what is the connection between inversion and stereographic projection? How are they related? Okay, they are related in many ways. In fact, when you have stereographic projection, okay, you can, by this process we explained how points on the sphere are corresponding to points on the plane. Now you can start to draw lines on the plane, and see how, what's their image on the sphere, and vice versa. You can have a circle on the sphere and see what is the image on the plane, and you will find that, in fact, lines or circles mapped to lines and circles, just like geometric inversion. Lines become circle or lines. Circles become circle or lines. On the sphere or on the plane. If you start to do these. So this example, for example, you have lines here, right? And those lines are actually mapped to circles. How can you know? Because you can see. You see this. Look at the green square. Okay, so you follow a line on the green square. So this line becomes becomes this line. They are circles. They are circles on the sphere. And also look at the border of this plane. You see, they become these four kind of arc of circles. But basically, you can prove, and it's not difficult to prove. You can see the proof if you go to Wikipedia, stereographic projection. You can see the proof that circles becomes lines or circles, and lines becomes they map it two lines or circles. Stereographic projection. Now, let me talk about how are they connected. First of all, just like inversion, lines become circle or lines. Okay, now let's talk about inversion in three-dimensional space. 5 more minutes, that should be it. Let's talk about three-dimensional inversion. Okay, so now we have talked about two-dimensional inversion, which we begin, we do inversion, geometric inversion on a plane. In a similar way, we can do inversion on three-dimensional space by imagine. So first of all, what are we doing? So imagine, so we have points in space, 3D space. We have a bunch of points. Now we want to do a transformation. So given a point, after the transformation, we will have a new position for that point. That's what transformation means. In this case, we are doing transformation in 3D space. Okay, and now the transformation we want to do is a geometric inversion. Now, just like two-dimensional case, we start with a circle. I mean not a circle, a sphere in three-dimensional space, and just like the 2D case, so given a point, we draw a line from the center of the sphere to the point, and the distance from the center of the sphere to that point multiplied by distance from the center to another point on the same line will be equals to r squared, where r is the radius of the sphere. Just like the 2D case, we can see the 2D case here, But imagine this is three-dimensional, where this circle is a three-dimensional sphere. So in this way, any point in space, will have a new position. So again, just like the two-dimensional case, any point outside of the sphere will be mapped to a point inside of the sphere. Now this is a three-dimensional case of geometric inversion. But okay, so how does it relate to stereographic projection? Now, the 3D case of inversion, I'm not sure I did a good explanation. You have to kind of imagine, you have to convince it yourself how it works. Am I like clear? Let me take a break and read the comments. So Norman says, speaking of geometry, ray tracing might be an interesting topic of future talk. Yeah. Ray tracing is it's more of a computer graphics related. In math you don't do that. Let me see, where am I? Am I still talking good? Okay. So Danielle says, people say that now non-Euclidean geometry is invented. Euclidean geometry is false. There is no certainty in it. No, that's bullshit. Okay, that's another topic about Euclidean and geometry and non-Euclidean geometry. They are all geometries. Okay, they are different geometries. They are different geometries with different axioms. Okay, they are all models of geometry. Now, when non-Euclidean geometry is first thought about, it's one huge chapter in history of math. Okay, it's like a shock among mathematicians because it was impossible to believe. Okay, but anyway, Euclidean geometry, non-Euclidean, they are all just models of geometry. We have different models. Now the questions to a lot of people is, which universe is our universe, Euclidean or non-Euclidean? We don't know. Actually, the answer is actually we don't know. So far, the science, the physicists, we actually do not know, and we actually don't even we don't know. I mean, there are a lot of questions. We don't know what dimension. Are we actually in fourth dimension, or are we in five dimension, or Then there's a question. By the way, there's also relativity, which is, by the way, Einstein's. It's related to time and space. That that combines time and space into one concept, inseparable. Like there's no different thing. Time and space is one thing. And by the way, that is actually different from the dimensionality we are talking about in geometry. Fourth dimension, fifth dimension, that's totally different. In geometry, it doesn't matter Euclidean or non-Euclidean. You have dimensions, and those dimensions are not related to time. It's not the time we are talking about. So in relativity, that time and space thing is again, it's a different thing. So we are getting complicated, into these advanced topics, and we to go into that, we need to explain what is Euclidean geometry, what is non-Euclidean geometry, and that's big topic. That's how you actually that's how you study. You get a PhD in math to begin. Well, you don't. You just need a degree in math to understand those things. So let me get back to the how stereographic projection is related to geometric inversion. In fact, stereographic projection, we talked about the way they correspond points on the sphere and points on a line on a plane, is actually a instance of geometric inversion in 3D. So how is that related? Let me just explain. I'm not sure I can do a good explanation now, but let me just do it. Let's go to a new tablet, okay, a new panel. So let me try to explain it in 2 minutes. Just to give you a flavor, and you can read up on Wikipedia. You go to the article stereographic projection. You'll see how stereographic projection is actually just a instance of geometric inversion in 3D space. That is why you see a lot of similar properties, such as lines becomes circles or lines, and circles become circles or lines. So imagine this is a circle. Okay, I'm not doing a good job. So this is a circle, and we are doing stereographic projection. Stereograph. Okay, there's a lot of lag here, so I cannot write well. But imagine this is stereographic projection. So we draw a line. So let's say this point is P and this point is Q. So that's stereographic projection, right? Imagine this is three-dimensional space. So we project the line from North Pole to any given point in the plane. And let me see. Okay, so we project. That's how we got our point Q. When the line intersect with the circle, I mean the sphere, we got a point Q intersection, and that is the image of P. P and Q are related in that way. Now imagine there is another circle twice as large. So I'm going to draw a circle here. I mean, not a circle, but a sphere. Imagine there is Okay, this is a bad drawing. Imagine this. Okay, let's. Uh, this is so bad. Uh, okay, I'm just gonna go on. Okay, and I'm not going to fix drawings. Imagine there is a circle twice as large. Okay, something like that, twice as large. So from here, this is R. Uh, this is R. This is R. This is R. So from this sphere has radius R, and this sphere has radius 2R. So and the larger sphere is centered on the North Pole. Now, now look at this line. Imagine we are doing okay, right. So we got this large circle centered on the North Pole with radius of 2r. Now we are going to do a geometric inversion of this point P and Q. I mean this point P. Now can you see that? You see, we are doing a geometric inversion with this point P with respect to this large circle. You will see that the resulting point is this Q, exactly the same as the process of stereographic projection with this small circle, small sphere. Now, that I just covered that. That's how they relate. Okay, they are the same thing. You might want to think about that, or go read Wikipedia. That is how they relate. So on this picture of stereographic projection, imagine there's a larger sphere, twice as large, and we want to do geometric inversion with respect to that large sphere. So any this point on the plane will become a new point, and this new point is on this sphere is actually just the point of the geometric inversion with respect to that large sphere. Okay, that's it. That's that's about it. That's it. That's what I'm gonna explain. Okay, I hope that's a good talk. I hope I did the job. 70 weeks, so we did 80 minutes. I hope I covered. So we have covered. Actually, we have covered the meaning of geometric transformation. We have covered the four fundamental geometric transformation. That is reflection, translation, scaling, and rotation. And this four is called isometry. We are covered, and isometry is a distance preserving transformation, a important property of geometric transformations. Okay, then we have covered in geometric inversion, which is a transformation, a geometric transformation. We have covered some important properties of geometric inversion, which is one, angle preserving, and also circles mapped to circles or lines, and lines becomes lines or circles. That's important, interesting property of geometric inversion. And we also covered how geometric inversion is actually kind of a generalization of the process of reflection. Because you can see anything outside becomes inside, anything inside becomes outside. It's kind of very interesting mirror, around a circle or a sphere. And we have also covered how the geometric inversion in three-dimensional space, just like two-dimensional space example. So instead of a circle, we have a sphere. Anything outside of the sphere comes inside. Inside comes outside. Then we have also covered the interesting concept of point at infinity, how it naturally arises. And we have this concept of point at infinity. Then we have also covered stereographic projection, uh, which is very simple idea. You look at the picture, you actually understand it immediately. How points on the plane and points on the sphere are related by a line. And this is another example of geometric transformation. In this case, it's a transformation between actually two different spaces. One is the Euclidean plane, another is a sphere. And we also have seen how a point at infinity concept occur here, because what happens if your point is at the north point? So we have a concept of point of infinity. And we have also talked about how this point of infinity in mathematicians' idealization, they become what's so-called Riemann sphere. And mathematicians call it Riemann sphere. Uh, so Riemann sphere, that's the jargon, okay. Uh, so that's what we have covered today. And finally, we have covered how stereographic projection is actually just it's just a geometric inversion in 3D space with a circle twice as large and centered on the North Pole. They are the same thing. Yeah. So let's see. Let's read a comment. So any more comments? Just type it. This is a good time, and we'll say goodbye. So Daniel says, is the universe Euclidean or not? The answer is that space is three-dimensional Euclidean because the concept is space. Space is just a mathematical concept. You can start with any meaningful math. What do you mean? Now, first of all, Danielle, do you have a degree in math? Like, do you have equivalent? Some of us may not have a degree, but we have realistically equivalent knowledge. Because a lot of mathematicians, some of the greatest mathematicians, did not go to college. For example, Fermat, who is famous for Fermat's last theorem, he does not have a degree, and actually quite a lot examples of mathematicians who do not have a degree. So Danielle, do you actually know this math, or are you just suggesting opinions? Because actually, if you want to discuss, Euclidean geometry or non-Euclidean and talk about whether we are in our space is Euclidean or space, you have to actually know the stuff. Because, if you are just curious, first of all, I don't have a degree, okay? So my math background, you might say, I don't have a degree in anything. I don't have a degree in computer science neither. So I don't actually have any degree. But I studied stuff. So, whether you trust my opinions is up to you. Just judged by what you already know in programming, maybe, so it's up to you. But to talk about these things, you kind of have to know math. So Danielle says, okay, you have a graduate degree, but let's make my point simple. That it's interesting stuff. Euclidean versus non-Euclidean. Yeah, Euclidean versus non-Euclidean is interesting. But what are you saying though? But what are you saying in your last comment? So Daniel says, is the universe Euclidean or not? The answer is that space is three-dimensional Euclidean because the concept of space okay, I don't know. I don't know exactly. I don't know. I don't know I don't know exactly what you mean in your comment, in your last comment about the Euclidean versus non-Euclidean and the space we live in. It seems you are saying that the space we live in is Euclidean 3D space because the definition of space. I'm not sure I agree or understand that. What do you mean? Because as far as I know, we don't actually know our space. By our understanding, the cosmology. I mean, the proper term for this study of whether our space is Euclidean or not is cosmology. It also relates to what dimension, how many dimensions do we have is our space, and also is it parallel universe because it's all kind of related. And as far as I know, I've read, I'm not a professional mathematician or a physicist or as far as I know, we don't know the answer. The top scientists, the cosmologists, we don't actually know definitely or agree upon, or the cosmologists, we don't have one solid answer whether our universe is Euclidean or not, and we don't know our universe is. We don't even know what's the topology, the shape of our space, and we don't know how many dimensions is our space. It's kind of all open questions. So that's what I think. So okay. So anyway, I think so. Danielle says space is invisible. Heck, all straight lines are invisible. They are one-dimensional. Space is invisible. The idea here is not to know if space is Euclidean. Math is not discovered, it's invented. Yeah, okay, again, that's veering into philosophy of math. Math is not discovered, it's invented. Yeah, okay, I guess we are touching on the philosophy of math then. Because then becomes there's the philosophy of math where whether is math already exists or it's just something we invented. Yeah, there's a bit quite contentious different philosophies of math. Yeah, that's getting complicated. Anyway, but so thank you guys for coming by, and thank you for your comments, Daniel. That's it for today. So I hope you guys have a good Monday. I guess Monday is a work day. Uh, yeah, if nobody knew the Pythagorean theorem yet, would it not still be true? Yeah, that's like saying, if tree falls in a forest, but nobody is there, do you still hear it? Yeah, so it's like in the realm of philosophy, kind of. And there's a Platonic school of, thought. There's log- logicism, there's formalism, there's intuitivist school of thought. Yeah, you kind of get into philosophy of math. It's a very interesting topic, by the way. Okay, have a good day, guys. I hope to see you next time.